Hi everybody, this is Dr. Bricker here with a video for chapter 22, which is on current and resistance. So we've been looking at everything sort of on a really small scale, forces between individual charges, electric fields, potential because of just small amounts of charge. Now we turn our attention to something much larger, current and resistance, that maybe you're more familiar with. It all really goes back to the principles that we've talked about, but now we're just going to look at it on a grander scale. So current and resistance. The next chapter is actually on circuits, so kind of the similar theme here for a bit. Okay, so the goal of this chapter is to learn how and why charges move through a conductor as we call current. Same kind of idea that we had before. Before we had electrostatics, things were not moving. Now we're going to allow groups of charges to move in something called current. And there is a resistance to the flow of charge, something called, as you might have guessed, resistance. So this person's actually measuring their content of body fat based on how much resistance. So fat has a different resistance than muscle, so this device is doing that, converting resistance into percentage of body fat, for example. So the motion of charges through a conductor is called current. There's some holiday lights lit up because current's flowing through them. So current, it's not some sort of magical current dust that you sprinkle on anything. It's because it's an electron, it has a charge, a whole bunch of electrons moving constitute a current. And electrons aren't destroyed, so neither is charge. Ohm's law, we'll get a kind of a taste of Ohm's law in this chapter, relates the current in this bulb to the battery's voltage. So just like we talked about voltage before, we're going to have it again in this chapter, but maybe look at it in sort of a macroscopic way. So the resistance to flow of charge, again, is something called resistance. Okay, so conductors allow charge to flow depending on what they're made out of. Some materials are better conductors than others. We've got gold, silver, copper, things like that. They don't all allow charge to move equally. So some are better conductors than others. Some are more expensive than others, so you're probably not going to wire your house in gold. You could. Hair dryer converts electrical energy into thermal energy. So we're going to take some electrical energy. What do we do with it? Lots of different things. One idea is thermal energy. Maybe you've got an electric blanket. It's the same idea. Okay, so you'll learn the relationship between electric power and current, resistance, and voltage. Okay, way back in the previous chapter, you learned that the connection between electric field and potential. The lab that you do this week is the same thing. So this is a capacitor, positive charge on one plate, negative charge on the other. The first way we looked at this was in terms of electric field. So the electric field goes from positive to negative. So if you were to put a positive charge in this electric field, it would experience a force in the same direction as the electric field. We also looked at it in terms of voltage. That's what these lines are, if you remember. Equipotential surfaces where they have the same voltage. So here we would be going from a higher voltage on this line to a lower voltage. So going downhill, and a positive charge, again, would accelerate this way. Turning electrical potential energy into kinetic energy. Just another way of looking at the same thing. So, model of current, if you connect two capacitor plates of a parallel plate capacitor, that's what we've been talking about most of the semester, with the piece of wire, the plates will become neutral. So negative plate over here, positive plate over here, you connect them and charge can flow now. You've given the charge a path. Negative charge, again, doesn't like to be by other negative charge over here, so it will flow to this plate which has a lack of negative charge, so it's positively charged. So you can discharge the capacitor. In doing that, this wire is going to heat up. If it was a light bulb, the wire maybe would even glow. Okay, so if we observe the capacitor discharge, we see other effects. The wire gets warmer, and you can tell. Literally, what's happening is the electrons are colliding with other particles in the wire and heating up. Now, if you were to take a light bulb and put it here, the light bulb would actually glow. So you've stored up some energy somehow in a capacitor, you connect it to a light bulb, and you can discharge the capacitor. You have it go through here. So you're not using up any electrons, they're just going from one side to the next, and when they do that, they go through the filament here and gets hot and glows. We'll see this chapter, this semester as well. If you have current moving, now current moving is electrons actually moving through a wire. If you put a compass around the wire, it's going to produce a magnetic field. So electricity and magnetism are two sides of the same coin, really. You can produce a magnetic field from an electric field. You could also produce an electric field from a magnetic field. It turns out a changing electric field produces a magnetic field and vice versa. That's the idea behind electromagnetic waves that we will also see this semester. Okay, so charges that move in a current are called charge carriers. So in a wire, in metal, it's electrons. In a solution, it could be positive or negative ions. But here in a metal, we've got some conduction electrons. And all metals are slightly different, so they've got different conduction properties. An insulator does not have free charges and cannot carry a current. So there's a sort of an in-between area between a conductor and an insulator called a semiconductor, which are made with sort of, I'm putting it in quotes, impurities that allow there to be some electrons available for current if certain situations are right. So those are kind of in a category by themselves, semiconductors. Other materials may have different charge carriers. Both positive and negative ions carry charge in solution. So you could have positive and negative ions if you have a solution, and then moving charge, that's what really makes up a current. Seawater, blood, intercellular fluids. Okay? So when we apply an electric field to a metal, the field exerts a force on the electrons and they begin to accelerate. We're going to start transitioning away from thinking about it really in this microscopic way. But really that is what's going on in your house. You're watching this currents flowing through some device, and really it's the force between charges that gets this whole thing happening. Okay, so really that is what's going on, but we can look at it in a more of a macroscopic, big picture way. Okay, second bullet point here, collisions between electrons and other atoms slow them down. Literally that is what's going on, they're colliding. Some of the kinetic energy that we calculated earlier in the semester turns into thermal energy, making metals warmer. Okay, so as long as you got the electric field there, you can guide electrons through. Now you might think the electrons move really fast through metal, and they don't. They move on like millimeters per second rates, and it's sort of a random walk. Electrons move, hit something, bounce back, move forward again, bounce back, and slowly make their way through a piece of metal. So they're not moving fast. Okay. Something called the drift velocity. They drift through. Oh, and here's a better picture of what I just said. So here's an electron. Now, electrons move in the opposite direction of the electric field, as you remember. Hit something, bounce back, eventually make their way through. Okay? So in a parallel plate capacitor, the initial separation of charges creates a potential difference. We saw how to do that. You make a potential difference. You connect the wire and you give the electrons a path to go. They can go from one side to the next. Right? They don't want to be by each other. They move from being grouped together to spreading out. Okay? So the potential difference creates the electric field in the wire, which then provides the force on the electrons. Okay, so in real life it's electrons moving, but there's something called conventional current where you think about it as positive charge moving. It doesn't matter, it's the same amount, but conventional current, people pretend positive charge is moving, but again that's not really what's happening. It's electrons moving. So you can see it here too. The electric field is pointing one direction, electrons are moving the other direction, from getting away from each other, going to this positively charged plate. Okay, so the current at point B is exactly the current at point A, right? The current is the amount of charge flowing through an area in a certain amount of time. So You got to have the same amount of charge here as here. None is created or destroyed. It doesn't. Some of it doesn't just stop somewhere. It just continues through here. It's kind of like if you turn on your garden hose. The same amount of water that goes in is the same amount of water that comes out. Something called the continuity equation. So the light bulb doesn't destroy them. They're not used up. They're just hitting other atoms and molecules, and that's what's heating everything up. No electrons are stored. They move through just like in a hose. No water is stored somewhere. Okay, good. So like an electric current and a light bulb, water flows through a turbine making it turn, just like electrons flowing through this bulb make it glow. It's the same exact idea. You don't use up water molecules to get this to turn. They just hit the turbine and make it turn. Same thing here. Electrons hit other molecules, everything's heat up by friction and glow. So the current is the same in all points in a current carrying wire, just like you got the same water flowing through a hose. Okay, so here's a conceptual example. The discharge of a capacitor lights two identical bulbs as shown. Compare the brightness. So these bulbs are identical. This capacitor is discharging, negative to positive. The same current goes through the first bulb as the second bulb, so they're going to be equally bright. Right? It's the same amount of current here, same amount of current here. So as the electron makes its journey through the wire, this bulb lights up, this bulb lights up. Same brightness. Okay, and that's a synopsis of what I've said. We've noted that the brightness of the bulb is proportional to the current it carries. So identical bulbs have the same current, so we've got the same brightness. Okay, it makes sense in what you've seen with a string of lights. It's not like if you have a string of lights, the first one's bright and the last one is really dim. They're all the same. It's the same current going through. No charge is used up. It's not used at all. Okay, defining and describing current. So capacitor discharges in the same way whether we consider negative charge moving opposite the field or positive charge moving in the same direction. So in reality, it's electrons moving. But if you thought about it as positive charges going the other direction, you would get the same total amount of charge. Okay, so this is something called conventional current. Current is the flow of positive charge. You can call it imaginary if you want to, because this is really not what's going on. But conventional current, people think of it as positive charge moving in the same direction as an electric field, from a higher potential to a lower potential. In reality, that's not really what happens, though. But we can think about it like that without losing anything. Okay, so currents are charges in motion, so we can define current as a rate, so in coulombs per second. So how many coulombs per second pass through a cross-sectional area here? So how much charge, that means how much charge, delta Q divided by delta T. How many coulombs per second? That's what current is. How many coulombs per second? And that's what we have here. So current is the amount of charge in the amount of time measured in coulombs per second, and we're going to see in a minute that a coulomb per second is a new unit called an amp. A-M-P. Just A for short. Okay, so whenever you see current described as amps, don't forget that really means coulombs per second. So I is used for current, delta Q over delta T. Okay, very good. That's our first formula from this chapter, actually. The amount of charge per time. Now, if you knew the total amount of charge per time, you could also figure out how many electrons that corresponds to. Okay, this is kind of a synopsis of what I've said here. So to figure out the total charge, then that would be the current times the time. Okay, so a synopsis of what I've said. Here's a quick check. Every minute, so every 60 seconds, we have 120 coulombs of charge flowing through this cross-sectional area. How much is the current? Let me switch this to a pen. So remember, current is charge per time. So we've got Okay, we've got 120 coulombs. Let's see if this will work. 120 coulombs in 1 minute. So 1 minute is 60 seconds. So that's 2 coulombs per second. And now a coulomb per second is an amp. Okay, so 2 amps. All right, good. Amount of charge in the amount of time. Okay, good. Here's an example. A 100-watt light bulb carries 0.83 amps. How much charge flows through it in 1 minute? So you could take the formula for charge, which was current, which was charge per time, solve for the amount of charge. So 0.83 amps, and an amp is a coulomb per second. Multiply it by 60 seconds to get 50 coulombs of charge. That's a lot of charge, actually. That's a lot of electrons, I should say. Why is it a lot? Well, we've got 50 coulombs, and 1 electron, magnitude of it is 1.6 to the minus 19th coulombs. Now, if you do the math here, you're going to have something to like the 20th power, if you actually did this, or more. So billions and billions of electrons. I'll leave this to you to figure out how many electrons this is, but it's a whole bunch. Understatement. Okay. So the current corresponds to a flow of a bit less than 1 coulomb per second, so our calculation seems reasonable. That's a lot of charge, as it says. The enormous charge that flows through a bulb is a good check on the concept of conservation of current. Okay? Very good. So this I will make a separate video for the homework. Okay? We can take a look at this problem, though. The discharge of an electric eel can transfer a charge of 2 microcoulombs in 2 milliseconds. What current does this correspond to? Okay, so I is the amount of charge in the amount of time. Just be careful with the units. The charge is 2 times 10 to the minus 3rd coulombs, and then this is 2 times 10 to the minus 3rd seconds. So the times 10 to the minus thirds cancel out, and we get 1 coulomb per second, 1 amp. Okay, so that's a lot of current. So don't get stung by an electric eel. That's a lot. 50 milliamps, if it goes across your heart, is enough to kill you. So this 1 amp is a lot. Okay, so as you know, current is conserved. We've got something called the junction rule here. So here's current going into a junction. Here's current going out of a junction. So however much current goes in has to be equal to the same amount that comes out. Same thing over here. You've got current going in, current going in. So whatever goes in has to be equal to whatever goes out. This is called Kirchhoff's junction rule. This will help us solve some circuits when we get into some more circuit analysis. So you can take whole semesters of circuit analysis and really get degrees in just working on circuits. We're just going to do it for a few weeks, so we get a kind of a survey of circuits. This is one rule, though, that will help us solve some of this. So if you're in some sort of MET major, maybe you've seen a lot with, or EET major, maybe you've seen a lot with circuits already. If you haven't, it's okay. We're going to spend a couple weeks working on it. Okay, so let's take a look at this one. The wires shown next carry currents as noted. Rate the currents IA, IB, and IC. Okay, well, let's see what we can do with this. So it looks like IA has to be equal to 2 amps plus IB, and then we know IC has to be equal to IB plus 3 amps. Okay, so I would say that IA has to be bigger, or sorry, IC has to be bigger than IA, right? Because you're adding 3 to IB. Here you're only adding 2 to IB. So I think IC has to be bigger than IA. And then we also know, because of this, how does IB compare to these? So IB must be the smallest, right? Because we're always adding something to IB to give us IA or IC. Like, for example, you take IB and you add 2 to it, that'll give you IA. You take IB and you add 3 to it, and you get IC. So I think this has to be the smallest of all of them, IB. Okay, let's actually see if we got that right. Good, IC is bigger than IA, and that's bigger than IB. That's an example of the junction rule. Here's another quick check. Let's see what we have here. Whatever's going into the junction has to be equal to whatever's going out of the junction. So right now, here's the junction. You have 7 going in and 9 coming out, and we don't know what's going on this part yet. But I would have to say that this would be 2 amps going this way, right? Because there's 2 coming in, 5 coming in. There's already 9 going out, so we must have more going in. So this must be 2 amps going in. So 2 amps moving to the left will make this picture make any sense. Okay, good. Conservation of current again. And then we'll do this when I make a separate homework help video. Okay, so a little bit about batteries. Batteries are kind of like a stair lift. Batteries take us from a lower level to a higher level. How can that be? Let's take a look. So a capacitor quickly runs out of charge, but a battery keeps its charge. So it's kind of, you can think about it as a ski lift. It's taking charge from one side, moving it up to the next side, and it's free to go through the wires and through light bulbs, whatever you have connected to it. Okay, so how does it maintain its voltage, EMF? Remember, electromotive force means battery voltage. So whenever you see EMF, sometimes it's squiggly E, that's how I write it, EMF. This means the voltage of a battery. Voltage of the battery. Okay, that's all it stands for. It maintains its voltage through chemical processes. So here's a battery. We're thinking about conventional current again. Really, it's the other thing happening, but we're pretending it's positive charge flowing. So here's the negative side of a battery. We're going to take positive charge and move it from this side. It doesn't want to leave here. We're going to put it to the other side, and then it's going to go downhill through the wire back to where it wants to be. So it doesn't want to go there. It doesn't want to go from down here to up there. So how does it actually do that? Through chemical processes. It turns out the positive side is called the anode, the negative side is called the cathode. And if you can make these out of dissimilar metals, one side likes electrons more than the other. And basically that's the idea behind it. So increasing potential. That's why I think it's kind of like a ski lift. Positive charge doesn't want to be up there. So we can get this happening, climbing up the stairs through chemical processes. So charges are moved from the negative terminal and lifted like a ski lift to the other side, and then once the ski lift gets you to the top of the hill, you go back down to the bottom of the hill. And then how do you get back up to the top? Well, you take the ski lift back up. The ski lift here is chemical reactions. So this charge escalator in a battery sustains the current in the wire by providing a continuously renewed supply of charge at the positive terminal. Okay, and then we've given the charges somewhere to go by connecting it all with the wire. So the charge escalator in a battery is powered by chemical reactions. Okay, chemicals are electrolytes are sandwiched between electrodes of different materials. They're dissimilar materials because one material will covet electrons more than the other. So we can set up the potential that way. Okay. A dead battery, on the other hand, is one where the supply of chemicals has been exhausted. Lots of research just goes into batteries, as you know. I mean, this electric cars, that's a huge research area right now. Not just in cars, but how do you store solar energy to use at night? So we've got to store it somewhere. Maybe batteries are a way to do that. I just listed this for a lead acid battery down here. I don't think you'll find this in the chapter, but here's one possible reaction. We've got lead, that's Pb, and an acid here and here. Different cathode and anode. One is lead, and then it looks like we have lead oxide down there. Anyway, you get charge carriers. You get the excess electrons, and that's what we want. So by separating charge, and charge escalator establishes the potential difference, the voltage. And as long as we have enough chemicals there, the battery stays charged up. Okay? And then we build up a voltage, EMF, squiggly E. That E just means battery voltage. So a capacitor stores energy. You separate charge and you use it quickly. A battery, on the other hand, maintains the voltage by chemical processes. So the rating of a battery, 1.5 volts, is the battery's EMF. So even if you have a AA, AAA battery, those are still 1.5 volts. Some are just bigger than the other and they've stored more energy, but they have the same voltage. C and D batteries, same thing, they're 1.5 volts. It's just that C's and D's are bigger, so they've got more, they keep it longer, that's what I'm trying to say. They're not more powerful, they just can store charge longer because they're larger. Okay, so the voltage across the battery is called the EMF. So if you connect batteries like this, you just add up the voltages. So negative, positive, you put them in something called series. So the potential difference for batteries in series, you just add them together. So this all added together would be 4.5 volts. Connecting it in series, one right after the next. Okay, so we've got 3 escalators piled right on top of each other. 3 ski lifts. You're going from one level to the next level to the next level. Okay, good. So wires inside devices connect AA's and AAA's together in series, giving us more voltage. So when you change the batteries in like your remote or something like that, you've got to put them in a certain way, right? One side has the spring, one side doesn't. You put them in there, and really what you're doing is connecting them in series. Okay, so I'll make another video for the rest of the chapter. So right now we've got the idea of charge, the amount of charge for the amount of time, coulombs per second, coulombs per second, which is equal to an amp. And now we've got this idea of voltage and what a battery does. Now we need to apply this to other situations. So I'll make a video for the rest of the chapter. Okay, talk to you soon. Bye-bye.